Hi everyone. So today we are going to talk about heat of reaction, and also another word for this is heat of formation, depending on what we're actually talking about. So I will explain what I mean in a bit. So the enthalpy of reactions. Now, enthalpy itself is the energy absorbed or released during a process. So in an endothermic process, we know that heat is absorbed. So if you know that you have a beaker and it has a reaction that's happening in the beaker and it's an endothermic reaction, that means that it's going to feel cold. And the reason that it feels cold is because heat is being absorbed by that reaction. It's taking the heat from your body and absorbing it in order to happen. So that is an endothermic reaction. Now, in an endothermic process, the products have more energy than reactants. So we write the energy on the reactant side because energy is going into the reaction to happen. So if we look at a kind of graph of what's happening here, the reactants have a lower energy than the products. And so since heat is absorbed in order for this to happen, our delta H is positive. Our enthalpy of reaction is positive. On the other hand, in an exothermic process, heat is going to be released. So it's going to feel warm, and the reactants are going to have more energy than the products. So the energy here is written on the product side because it is a product of the reaction. We're releasing energy. So if we look at a graph of what's happening with an exothermic process, we have a higher energy in our reactants, and then it's going to release that energy. So the products have a lower energy than the reactants do. And our delta H is negative because heat is coming out of the system or energy is coming out of the system. So again, looking at those signs of our enthalpy or delta H, in an endothermic process, energy goes into the system. So our delta H is positive. And then in an exothermic process, energy is coming out of the system. So delta H is negative. Think of it as like losing energy, right? So we have a negative delta H. Now, when we're talking about enthalpies of formation for specific substances, these things are going to be constants. And I gave you this table in class. So these are all our standard enthalpies of formation. So you can see some of them on this table right here. We can see that acetylene or C2H2, the enthalpy of formation for that is 226.7 kilojoules per mole, and it's a positive number. So what this means is it takes 226.7 kilojoules of energy per 1 mole of acetylene that's made. So it is an endothermic process because that delta H is positive. Now, on the other hand, ammonia, which is right under it, that NH3, that's a negative delta H. So we get a negative 46.19 kilojoules per mole. So what this means is that per mole that's made of ammonia, it's going to release 46.19 kilojoules of heat energy. All right, so that's what those positives and negatives mean. Again, these are standard. These are constants. So you can either just use your table that I gave you. You can also look these up online if you're missing your table or something like that. So when we are solving for enthalpy of something, again, that is represented by delta H, and this is going to be the heat of formation of a substance like you saw on that table. We can also use it to find the enthalpy or the heat of a reaction. So we'll do that in a bit. So when we find it for the heat of reaction, we're going to use this equation. So just like our delta T, our change in temperature, is final minus initial, when we're finding the delta H, the enthalpy of reaction, it's going to be final minus initial. So the enthalpy of the products minus the enthalpy of the reactants. So final products minus initial reactants. So when we are finding these things for a reaction, again, they are constants for substances. So you can get them from your handout, the table that I showed you before on the previous slide, or you can look them up online. Now, for example, if I want to find the enthalpy for this reaction here, the first thing I would do is I would look up the different enthalpies for carbon, hydrogen, and methane, CH4. So this chemical reaction shows that when carbon and hydrogen gas react, they form methane, which is CH4. So the first thing we do is we look up our delta H's, our enthalpies of formation for carbon, hydrogen, and methane. So if we look up the heat of formation for both carbon and hydrogen, You can look at your table, you can see that they're both 0. Now, the reason that they're both 0 is because those things are in their elemental form. That's how they exist in the world. It's not going to take any energy to make them. They're not going to release energy when they're made because that's just how they are in everyday life in the world. Okay. So our delta H for those two things are both going to be 0. Now, if we look up the heat of formation for methane gas, CH4, we can find that it equals a negative 74.9 kilojoules per mole. So because of this, we know that since it's negative, it's an exothermic process, right? It's releasing that heat. So if I'm going to find the delta H for this reaction, it would be the delta H of the products, which in this case is just methane, so negative 74.9 kilojoules, minus the delta H of the reactants, which is both 0. So the total delta H for the reaction is going to be negative 74.9 kilojoules per mole. So this means that this process, this reaction, releases 74.9 kilojoules of energy per mole that reacts. So it means that it's an exothermic process, and therefore we're going to write the energy on the product side because, again, it's releasing that energy in this process. So if I write my balanced equation, it is carbon plus 2 hydrogen gas reacts to form methane. And again, that little g means gas as well, plus 74.9 kilojoules per mole. So again, that's written on the product side because it is releasing that energy per mole of substance that reacts. So let's do a little bit of a harder one. So here we have a bigger reaction. So the first step here is that if we want to find our enthalpy of reaction, we need to find the enthalpies of every single thing that's in this reaction first. So we would look at our table, and then I can see that, of course, we just used this one. So the enthalpy of formation for methane is a negative 74.9 kilojoules per mole. For oxygen, it's going to be 0, again, because that is its elemental form. For carbon dioxide, if we look at our table, it's a negative 393.509 kilojoules per mole. And then for water, it is a negative 241.818 kilojoules per mole. So again, these are all constants. They can all be found on your standard enthalpies of formation table that I gave you in class, or you can look them up online. So we're going to use these now in that equation from before. So in this case, for our delta H, or our enthalpy of reaction, it's going to be, again, products minus reactants. So the products in this case are carbon dioxide and water, and the reactants are methane and oxygen. So writing those into this equation, I get delta H of carbon dioxide plus 2 times the delta H of H2O. And the reason there's a 2 there is because there are 2 of these things being produced when 1 carbon dioxide is produced, right? Because of our balanced equation. So remember, this delta H enthalpy is in kilojoules per mole, which means that per 1 mole, that's how much energy it requires to be made, or energy that's released when this thing is made. So because there's 2 moles of hydrogen here, because of that coefficient of 2, you have to make sure that you are multiplying your delta H of H2O by 2 as well. So whatever their coefficient is, you want to be multiplying that in your equation, minus the delta H of the reactants, which of course is delta H of methane. It's just one of them because the coefficient is 1 here, plus 2 times the delta H of oxygen. So now, using those enthalpies of formation from the previous slide, we can then plug in our numbers here. We get delta H of the reaction is equal to negative 393.509 kilojoules per mole, which was the enthalpy of formation for carbon dioxide, plus 2 times that negative 241.818 kilojoules per mole, which was the enthalpy of formation for water, minus my negative 74.9 kilojoules per mole, because that is the enthalpy of formation of methane, plus 2 times 0, because the enthalpy of formation for just oxygen is 0, because that is its elemental form. So doing the math here, we end up getting that the enthalpy of reaction is a negative 802.245 kilojoules per mole. So this is negative, which means that it's releasing heat, which means that it's an exothermic process. So what we're going to do is we're going to take this energy and we're going to write it on the product side because it's a product of this reaction here. Okay. And of course, this, if you look at this reaction, it is a combustion reaction. So we know that it's going to be releasing energy. So we write that energy into the reaction. So we get methane CH4 plus two oxygens, O2, reacts to form carbon dioxide plus two water vapor, H2O, plus that energy, 802.245 kilojoules per mole. So when we're finding our heat of reaction, you're going to use this equation, your heats of formation table. In order to do that, remember it's always final minus initial, the delta H of the products minus the delta H of the reactants.